Assalamualaikum and hi everyone. We are from Group 7, Section 6. In this video, I would like to present about our group assignment for numerical method. We choose Chapter 2 as our assignment. Our group consists of 4 members, which are Naziha, Nur Mahfuza, myself, Nurul Faiza, and Siti Salwana. So in this presentation, we will going to talk about introduction, methodology, result and discussion, as well as the conclusion of our findings. I will start with introduction. There are 2 ways to solve linear equations, which are Gauss elimination and Gauss elimination with pivoting. The Gauss elimination method is a systematic approach for solving linear equations. It includes converting a system of equations into an equivalent triangular form using a set of elementary row operations, such as adding multiples of one equation to another, or multiplying an equation by a constant. While Gauss elimination with pivoting is an expression of the Gauss elimination method that tackles possible numerical stability and accuracy difficulties. We used an experiment that was conducted by Polytechnic students, and the circuit was taken as a reference to this assignment.
Manual calculation. The first method, we will use Gauss elimination method. Firstly, we need to rearrange equation that we get from the circuit. Next, we need to eliminate x1 from R2 using the formula so it can become 0. Because of A21, A31 and A32 already 0, so we can simply use calculator to get the value of I1, I2 and I3. The second method is Gauss elimination with pivoting. The step is slightly similar. Firstly, we need to rearrange equation that we get from the circuit, but we need to swap R1 and R2. After that, just do some step like Gauss elimination method, which is eliminate x1 from R2 using the formula and find the I1, I2 and I3 after A21, A31 and I32 become 0.
So now I would like to present about our simulation using MATLAB. So this is the Gauss elimination. So we start from the line 1, which is the info here is to present the coefficient matrix of the system of linear equations, and B represent the right hand side vector. A is formed by concatenating info and B horizontally, resulting in the augmented matrix, which is info B. So next we go to line 4. So this is a nested loop structure, implements the Gaussian elimination. So it iterates through each row I from 1 to the number of rows in A. For each row I, it iterates through the subsequent rows J from I plus 1 to the number of rows in A. So the key one, calculate the multiplier needed to eliminate the ITH column entry in row J. And now we look at the row 7. It is to update the JTH row by subtracting Q1 times the ITH row from it. This step effectively eliminates the ITH column entry in row J by making it 0. After completing this loop, the matrix A should be in upper triangular form with the coefficients modified to reflect the elimination process. So next we go to the line 11. This part of the code performs back substitution to find the solution vector x of the system of equation. It starts from the last row of the augmented matrix A and works upwards to solve for each variable. So now look at the line 13, which is the HG is to compute the sum of products of the elements of row I excluding the last column, which is the right hand side B, with the corresponding elements of X, the already computed parts of the solution vector. And next to the line 14, xi is then computed using the formula that state in line 14, which isolates the variable corresponding to row I. So the last one, line 13, is this line is to print the solution vector x to the console. Next is the MATLAB simulation by using pivoting method. So we start from the line 1. In this section, A is represent the coefficient matrix of the system of linear equation, and B is the vector of constant on the right hand side. Augmented combines A and B horizontally to form the augmented matrix, where the last column of augmented represents the constant vector B. So next, the line 11, we perform the Gaussian elimination with partial pivoting. So partial pivoting for each column K from 1 to n minus 1, it finds the row max underscore row with the largest absolute value in the KTH column from row K to n. This helps to avoid division by very small numbers, which can lead to numerical instability. So the row swap, if the row with the maximum value max underscore row is not the current row K, it swaps the KTH row with max underscore row to perform partial pivoting. And for the Gaussian elimination, for each row I from K plus 1 to n, it computes a factor to eliminate the KTH column element in row I. It updates row I by subtracting factor times row K from it, ensuring that the KTH column below the diagonal becomes 0. So next, the back substitution. Starting with the last row, it calculates x and directly using the formula derived from the upper triangular matrix augmented after Gaussian elimination. And then the backward substitution iterates backward through the rows I from n minus 1 down to I. For each row I, it computes xi using the already computed values of x and the corresponding row elements of augmented. So the last one is display the solution. This section simply display the computed solution vector x to the console.
For manual calculation, mesh analysis were used to find the linear equation of the circuit. Mesh analysis is a technique used to investigate electrical circuit. Kirchhoff voltage law (KVL) is used to determine the current in the circuit loop. The linear equation from mesh analysis then rearranged into matrix form to start the calculation. Then, the S1 then eliminated from R2. After that, the equation then solved to obtain the value of I1, I2, and I3. While for the Gauss elimination with pivoting, the same linear equation was used and inserted into the matrix form. Then, the matrix were rearranged by swapping the R1 and R2. After that, S1 then eliminates from R2, and finally, the equation was solved to obtain the value of I1, I2, and I3. For Gauss elimination simulation, info is the matrix containing the coefficients of whatever in equations. B is the column vector carrying the constant on the right side of the equations. Constantly, info and B horizontally yields A. The nested for loop go through each row and column J of the augmented matrix A. The code generates the key K1 by dividing the element in row J and column I by the element in row I and column 1. It then subtracts a multiple of row I from row J, eliminates the element in column I below the diagonal. The code initializes the solutions vector as with zeros. It iterates backwards through the rows of A, beginning with the final row. For each row I, it computes the sum of the products of the rows coefficients and the corresponding x values. It then solves for xi with the formula xi equal to ai and hg divided by aii. Finally, the function outputs the solution vector I For the Gauss elimination with pivoting simulation, first we correctly define matrix A and B. Each row A corresponds to the coefficients of the variables in the equations, and B is the constant vector y in H. Matrix creates the augmented matrix A, B by horizontally concatenating A and B while partial pivoting has been implemented within the first loop k equal to 1 and minus 1. This assures that the pivots element in the largest element in the column, preventing division by very small values, which can cause numerical instability. Gaussian elimination was then implemented appropriately within the nested loop for I equal to k plus 1, and this phase converts the matrix to an upper triangular form. Finally, after Gaussian elimination, we use substitution to solve for x. Then, the value of x will display on the window. In conclusion, the values obtained from manual calculation for Gauss elimination and Gauss elimination using pivoting yields the same results. Typically, Gauss elimination without pivoting can result in substantial mistakes due to numerical instability, but pivoting helps to maintain accuracy by rearranging equations to minimize error build-up. However, in this scenario, both methods produce equal outcomes because pivoting is unnecessary. The simulations of both methods get the same results. It is because the simulation technique used for Gauss elimination with pivoting is not sensitive enough to the benefits of pivoting. It may not produce significantly different results than Gauss elimination without pivoting. As a result, both methods from both manual and simulation give the same answer.